Am I audible to you, sir?
Yes, yes. Hello?
Yes, sir. Yeah,
Mhm.
you are audible. Okay. Good morning to all participants, speakers, and faculties. We are honored to have Dr. Manoj Singh Parihar, sir, for this session. First, let me introduce to Dr. Manoj Singh Parihar. Dr. Manoj Singh Parihar received his PhD from the Indian Institute of Technology, Delhi in 2012. Currently, he is working as an assistant professor as an associate professor in the Department of Electrical and Electronics Engineering at the ABV Indian Institute of Information Technology and Management, Gwalior. Prior to starting his academic career, he worked as a senior project scientist at the Center for Applied Research in Electronics, IIT Delhi, from July 2010 to March 2013. From 2013 to 2024, he worked as a faculty of Electronics and Communication Engineering at the Indian Institute of Information Technology, Design and Management, IITDM, Jabalpur. He is a recipient of IETE SMT Ranjana Pal Memorial Award 2024 for his contribution in RF and microwave field. In October 2007, he received Institute of Electronics and Telecommunication Engineer Research Fellowship for his research work on reconfigurable antennas. In 2007, he was also selected for the university training program sponsored by the National Institute of International Education to visit South Korean industries and universities. He has published over 100 research papers in the referred journals and conference proceedings. His area of interest are reconfigurable RF printed circuit, passive and active microwave integrated circuit, microwave and millimeter wave device characterization, RF energy harvesting, and RF MEMS. Now, once again, welcome you, sir, for this session. Over to you, sir.
Yeah, so first of all, very good morning and thanks for a nice introduction. So today I'm going to deliver talk on this recent developments in antenna systems. Basically, I will try to cover some designs for 5G and beyond 5G applications. And you can see the talk is very much aligned with the theme of this MDP program, recent trends in antenna design for 5G and 6G applications. So first of all, I would like to thanks the organizing team to inviting me for this wonderful platform sponsored by EICT Academy MNIT Jaipur. So myself, Dr. Manoj Singh Parihar, I'm working as a associate professor at IIIT in Gwalior. So in this talk, what we are going to cover, we'll start with the brief introduction of IIIT in Gwalior, then our department, IEEE department. Then some basics of antenna systems, followed by the current technology available uh, in terms of antenna or radiating systems, or what are the solutions available to, I mean, to cater the demand of industry in terms of antenna systems. Then what are the futuristic technology which, I mean, will be employed in 5G or beyond 5G or communications. So this is our institute, Indian Institute of Information Technology in Gwalior. So this is first and one of the five centrally funded IIITs set up by the Government of India, by Ministry of Education, and like NIT, like NIT Jaipur or other NIT or IIT, it's also holds the Institute of National Importance, right? Um, so other than this Gwalior, we have other four IIITs under the same umbrella, like IIIT Allahabad, then IIIT Jabalpur, then IIIT Kanchipuram, then recently opened this IIIT Kurnool. So we have five institute which are fully funded by the government of India. And all five IIITs has different themes. So basically, the Gwalior is basically meant for IT and management. Then Allahabad is mainly for IT education. Then other three IIITs like Kanchipuram and Kurnool, they are mainly focusing on the design and manufacturing part, right? So, IIIT Gwalior is a basically specialized research and academic institute to offer high quality education in field of IT and management. And the institute offers bachelor programs, master's program, and PhD programs in different branches like EEE, then CSE, then mathematics and scientific computing. In addition of this, institute offer 5 years integrated program also leading to I mean IMT and IM basically it offers BTech plus MTech and BTech plus MBA program. It's a 5 years program. In addition of these two integrated program, institute also offer the regular MBA program. The department, so the department of EEE was not very old. It was established in 2022 and is to offer high quality education in electrical and electronics engineering to meet the demand of no industry or current requirement of the industry. Besides this, it has strong research programs, PG programs related to masters and PhD in the major area of electronics and electrical. So as far as the department, that department offers 4 years BTech EEE, then 2 years MTech program in IC design and technology. Then from this season, we are also starting this program in autonomous systems and machine intelligence. Then PhD programs in the different areas like RF, microwave, photonics, antenna, VLSI design, communication, signal processing, and control and automation. Besides this, our institute also offer postdoctoral positions in various emerging area of EEE. And as far as the department strength, we have a highly qualified 17 full-time faculty member. And in addition of this, we also have 6 adjunct faculty member. They are renowned persons from the academia and in industry, right? So as you see, the department is not old. It was started 2 to 3 years back. Still, we have no significant faculty strength, right? In addition of that, we also have the 30 PhD scholar, including full-time and part-time. And also we have the master's students also. They are working on the different areas of the electrical and electronics engineering. So this is all about the department. Now let's start the talk. So as we are talking about the antenna for 5G and 6G or beyond 5G communication. So what are the evolution or revolution in terms of G technology, right? So we started way back in 1980s with the voice calling facility. So this was basically first generation communication system where we have the trunk call, we have to dial the trunk call. Then we see basically a wired communication. And you can see it was introduced in 1980s. So the voice, we have only voice calling feature, and you can see the cost was very high. It's close to 0.1 USD per minute. Right. Then the mobile phone introduced in 1990s with the 2G technology. So addition of voice calling, it also has the this texting or text message facility. And this the cost of this calling is down to 0.05 USD per minute. Right. Then the smartphone introduced. Not a smartphone. It's basically you can say semi. So you can have some web browser also. Right. So it has internet access facility. It was 3G phone or 3G technology. It was introduced in 2000. So now we have started talking about the data transmission, right? Because you have the data when using the internet. We talk about the data, right, mainly. So Then the cost reduced to 0.1 USD. Now we're stating about the cost of data, right? Or cost per unit of data, right? So the cost was 0.1 USD per MB. Then we had the actual smartphone in 2010 with the introduction of the 4G technology. So data transmission rate and we reduced to 0.1 USD byte per GB. Earlier it was in 3G, it was per MB, now it's per GB. Then we recently we have the 5G technology. It was introduced 2020, and very recently it's deployed throughout the India, right? So now we are talking about how many devices we can connect with this 5G technology. So number of instead of talking about the data, we started talking about the connection links. So and the cost is drastically reduced to from 1 USD to but per terabyte, right? So then now we have the 6G technology. So we expect that this 6G technology will be deployed by 2030. So now we have the more than, it's not about the communication or not about the calling. It has so many features we are going to have with the 6G technology. So we can have more number of devices to be connected compared to the earlier technology like 5G. So this is all about the evolution of technology from 1G to 6G technology, right? So what is 5G and 6G technology or beyond 5G? So this 5G is the fifth generation technology of the mobile network. It's basically a successor of earlier technology like 4G or LTE or preceding technology like 3G, 2G or 1G or 2.5G. So what are the key features of this 5G, right? So you can see, you can expect very low latency, close to 1 millisecond, then very high data rate that can go up to 10 to 20 Gbps, maximum it can go, right? And you can see it is 10 times more than the 4G. But the practical speed will not be 10 to 20, but it's very close to 0.1 to 1 Gbps we can expect. Then the number of devices we can expect it is, and the connection will be 1 million devices maybe per kilometer square area and with higher capacity, right? So this is the scenario of the 5G. You can see here. So many devices are connected with the 5G technology. So you can see here the healthcare services are connected, then smartphones are connected, then this virtual reality kind of things we can have with the 5G technology, then smartphones, then we can know that everything is now in terms of education, everything is online. So we can have the good online education platform, we can connect in the real time, right? Then we can also have the smart energy meters, right? So we can monitor all these things with the 5G technology. So what are the key applications and use cases for this 5G? So we can have you can see this figure, we can have the IoT, agriculture or industry. And we have application in all these areas, home automation, safety, right? And this is all about the machine to machine communication. I mean, we are trying to connect everything, right, with this technology. In terms of communication, it can provide very ultra reliable, low latency communication. So this is required mainly for this transportation, right? Or we can make it more intelligent by using the 5G technology. Then vehicle to communication or vehicle to infrastructure communication, right? So by using 5G, all will be connected to each other and also at the same time will be connected to the base station or maybe other networks, right? So we can have the concept of autonomous driving. Then, this industry 4.0 and beyond. So this is all required, this 5G technology. Then as I mentioned, this is also required for the healthcare, right? Then enhanced mobile broadband. So we can have the concept of smart offices. You can you can experience very high definition videos, okay, or you can enjoy this AR or VR features. Then education, you can have this sports event capturing in a real time. Then also it's very useful for safety and security purposes. So this is all about the few important application of 5G. Then the 6G communication. So what is 6G basically? So the 6G is the successor of 5G technology, and it will be able to use higher frequency than the earlier technology like 5G networks, and it will provide substantially higher capacity and much lower latency compared to the earlier technology. So what we expect so data rate or speed may go up to 1 Tbps. Then what are the key technology behind this 6G, right? So we can have a terahertz based communication or a joint communication which can communicate as well as sense the things, right? Then we can also integrate the technology with the AI and machine learning. And also we have the concept of RIS in terms of, so these are the key technology behind to implement the 6G technology fully, right? If we talk about the applications of 6G, real application, so we can have an addition of this AR, VR, we can have truly immersive extended reality XR, right? And we can experience the actual world, right? Through your this headset, right? Then you can generate the mobile holograms, and then you can create digital twins. So you can see all these images are there, which can explain the application of this 6G technology. So you can have you can see here the actual application of this, like this AR was, I mean, main feature of 4G. Then we have the 5G, like VR. So you can see here for AR, we only require the one handset. You can mimic your surrounding words in virtual form using your mobile handset. Then we have the virtual reality. You can realize everything, whatever available, right? You can just create the replica of the actual world through the virtual world using this headset, right? We have the concept of mixed reality. In this, you can have the presence of actual world or a surrounding, right? Actual surrounding, the things which are surrounding to you. You can actually experience, like you can enjoy playing the football match, right? Like sitting in the football stadium or whatever you can realize using this concept of the mixed reality, right? So it's basically combination of AR and VR. Okay. Then you can also create the digital twins, like it is required. Suppose you want to have the maintenance of aircraft engine, so you can, by creating the digital twin, you can easily maintain and repair your this physical objects, right? So this will be cost effective and time saving, right? Then you can also feel the presence of real thing by using the concept of haptic internet. So you can feel the presence, you can smell the presence of whatever you want. You can just remotely you can feel the touch, or you can feel the presence of your actual maybe your family members or relatives. Then we have this intelligent wearable devices. You can see here you can, using this band, you can integrate so many things, right? And this is very useful for the security and health application point of view. You can monitor your vital parameters, right? You can provide a real-time data, right? So this is all is possible using the sixth generation communication. So when we talk about the very important, what is the spectrum for this 5G and beyond 5G technology? So the spectrum which is being basically focused for this 5G, there are two bands are assigned for 5G communication. One is FR1 band, that is sub 6 gigahertz band, or we can also call it for early 5G application band. Right. So this band extended from uh, 3, 4 3.4 gigahertz to 3.6 gigahertz, centered at 3.5 gigahertz. So this is the entire spectrum, as you can see here, divided in a sub 6 gigahertz band or a 5G millimeter wave band. So, but due to some issue, we are also using the second band, that is high frequency band or a millimeter wave band. This is FR2 band, and the frequency is assigned for this band is at 24.9 gigahertz to 29.5 gigahertz. And we'll see soon that why we're switching to the higher frequency band, because this band has some limitations. So that's why we are thinking of using higher bands to get them more features from the 5G technology. Then the spectrum for 6G will be in addition of lower bands. like FR1 band, or which is being used for 4G or LT technology, will also be utilized for a 6G communication. This band is from a 4110 megahertz to 6 gigahertz. Then 5G new radio band, that's for 4110 to 7.125 gigahertz. Then FR2 band will also be utilized for a 6G, that is from a 24.25 to 52.6 gigahertz. Then what is new basically? So this new band is a FR band or 2.0 band. That's from 7.125 to 24.25 gigahertz. And also the very new things is new addition is this sub terahertz band we are going to utilize for the 6G technology, which was not in case of earlier technology like 5G or 4G technology. So this is the some application advantage or disadvantage of using this sub 60 gigahertz band or FR1 band for 5G applications. So this band is used for a variety of communication applications. This includes basically cellular network like GSM or Wi-Fi band and Bluetooth, WiMAX, WLAN, and other wireless technology, right? So you can see this band is very much congested, right? Because of so many applications are there. So there's a chance of no. So basically, when we talk about the 5G sub 6 gigahertz, this is somewhere here, right? So look at centered at 3.5 gigahertz. So the point is, this band is this sub 6G band is highly populated, right? Because of the so many applications are there. So there is a chance that this is lot of no interference will be there from the surrounding bands or from the nearby bands. So, but at the time we have the advantage, we have the limitations also. So, what are the advantages with the this 5G? So we can have, since frequencies are relatively low, so we can have a good coverage or we can have the high penetration, right? Then versatility is there because no, this frequency is not very high, right? So the point is we can also, to some extent, we can use the this existing infrastructure, right? We can use the existing infrastructure. Then it is also cost effective, as I mentioned. This is not, we don't require much change in the existing infrastructure. This is cost effective, and we can have the moderate device compatibility. I mean, we can connect the our existing system to the other systems, right? Then at the same time, we also have the some limitations. So what are the limitations? Limited bandwidth, because the frequency is limited or frequencies we have the limited bandwidth. Then because of the so many bands are there, the spectrum is maybe there is a chance of interference from the other band. Then this band is very congested, and we cannot connect so many devices. So this is limitation of connecting many number of devices. Then millimeter wave. So due to the limitation of the early this sub 60 years when we are planning to and we are switching to the higher frequency band. So this band is typically used for high speed communication networks such as 5G cellular network or FWA or other point-to-point communication. So this band is actually from 24 to let's take 100 gigahertz band. So the advantage, we can have high data rates since frequency is high, or when it is we can have more bandwidth, we can have the high data rate with a low latency. So since we have a higher bandwidth, we can have the high capacity and it can support massive connectivity, right? At the same time, there are also some limitations are there. So we have the limited coverage because of the high, high losses of the signal that moving to the high frequency. So it has also have the limited range. Then blockage issue will be there, fading issue will be there. Then power consumption, and as I mentioned, we are switching higher frequency, so we need to change everything. So it involves high infrastructure cost involved by moving to the high frequency band. So while moving to the 5G or beyond 5G technology, there are so many challenges while deploying this 6G or 5G technologies. What are the challenges we will be facing? The infrastructure requirement, right? If you're the like millimeter wave technology or like terahertz technology, okay, you need to change everything. Right? So mobile devices need to be upgraded. Then always there is a doubt of a return of the investment or cost. Then signal blockage will be there, right? So we need to, have so many towers, right, to cover the required distance, to cover the required users. Then security and safety will also be there. Then how this 5G and 6G technology will be compatible or can be integrated with the existing technologies. These all are the challenges lie behind the mm, by deploying the 5G and 6G technology. So now we come to the antenna, right? Because this FDP is focused basically antenna for 5G and 6G technology. So let's talk briefly about what is antenna. So you maybe all are aware the antenna term because many are from antenna background or RF background. So I assume that all are familiar with the antenna, but still, okay. So how did the antenna evolve? So the symbol of antenna, you can use something like this. So what is antenna? So it is something which can be used to detect or feel or sense the signals surrounding uh, of your surrounding things, right? So you can see here there's many insects are there which used to sense the signal, surrounding signal, or can use to sense the signal, or can use to communicate with the environment, right? So they have the two kind of feelers, right? So you can see butterfly, then you can see honeybee, then ant or grasshopper, then snail. So they all used these feelers to sense the environment, to communicate with the environment, right? So from here, this concept of antenna was evolved, right? So then it is, we can call it aerial, or we can call it antenna and then radiator. So technically, how we can define? So it's a basically very, very indispensable element of the transmitter and receiver, which used to transmit or receive radio signal. Radio signal into the space, or can receive the signal from the space as per the IEEE definition. Or you can, this as a interface between a circuit medium to free space, or guided medium to unguided medium. Or we can also call it impedance matching network between the transmission line and free space. Or you can call it transducer, which can convert time varying voltage and current into time varying radiated electric field and magnetic field, or vice versa if you're talking about the receiver mode. So it's basically, also we can call it a region of transition between guided EM waves in transmission line into freely propagating EM waves in free space, or vice versa, with some specified directional properties. So this is the overall antenna system. So see here, to excite your antenna, we need the high frequency source. Then we need some kind of guiding structure, maybe transmission line, or maybe optical fiber, or whatever you can think of. Then this is the antenna which can convert, which can act as an interface between the free space and your guiding medium, that is basically transmission line. So it's provide the impedance matching also between the free space and your transmission line, right? And it helpful to launch the fields from the transmission line to the free space. Okay, so you can see also within your antenna, the fields are basically in the form of lines, but when it is thrown to the free space, it's form a kind of loop, right, to survive in the free space. So this is the transmitting system, and this is the receiving system. So the wave which are launched from the transmitting end may be captured by the similar kind of antenna using at the receiver side. So again, this receiver antenna will convert this loop or loop of electric fields or magnetic fields into this electric field line or magnetic fields line, or can provide the matching, impedance matching between the free space to the transmission line, and finally your signal will be delivered to your RF detector or maybe any board, right? And you can mimic this. You can have the analogy of the system like this boy. So you can see this boy can act as source of signal or source of energy, and this ring can act as an antenna, right? And this you can see. So you can see here when this up to this ring, this bubble is in the form of, this in the form of open surface. Once it is detached from this ring, it's form a closed sphere, right? So you can see this can have another from this system to this toy. So what are the conditions required for the radiation, right? So we require the very high frequency signal, voltage or current, or time varying voltage and current. In addition of this, what we required is basically abrupt change or more discontinuity in the shape of your radiating element. Right. So when there is a abrupt change in the, or there is a discontinuity, there will be a acceleration of charges or a deceleration of the charges. So it leading to the radiation into the free space. Then also in addition of these two requirement, we also need a systematic design for the elements. Like what's the size of antenna in terms of wavelength, the lambda by 2 or lambda by 4. It depends on that kind of antenna. You always try to design your antenna as per the given requirement, like specifications, material specifications, or what is your input signal, or what the frequency of input signal. So you keep all these in mind while designing your antenna. You have the efficient radiation. So these are the pioneers in the field of antenna, contributed a lot in terms of antenna or in antenna technology or antenna knowledge, right? So our Indian scientists, and J.C. Bose, then Maxwell, then Hertz, then Marconi, then you may be aware with the this Yagi antenna, which was invented by H. Yagi. Then you may be aware with the very famous book by J.D. Cross, then Professor Mitra, then Balanis. Most of you are aware with the Balanis antenna book, right? So these are the prominent figures in the field of antenna technology. So what are the enabling technology for 5G and beyond 5G technology, which we are going to discuss? So what are the concept or existing solutions? So we have the multi-beam antenna or a multiple beam antenna technology, then MIMO, then massive MIMO, then beam forming and phase directed antenna, then a reconfigurable or active or rectifier integrated antenna systems. So then recently there's a lot of tension is going on this RIS or IRS kind of structures. So what is multi-beam antenna technology? So multi-beam antenna technology. So this antenna, I mean, multi-beam antenna are capable of transmitting or may receiving multiple number of concurrent but highly independent or highly directed beam to cover the predefined angle range. And they provide a solution to overcome the issue of limited coverage of the single beam system. So this is the scenario, right? So by using this multi-beam antenna, we can cover multiple regions, which is not possible in case of single antenna, because single antenna can transmit the, or single beam antenna can transmit either single beam or broad single beam, right? So it can cover users to the limited range of the organization, and at a time only a single user can cover. But using the concept of multi-beam antenna, we can cover the multiple number of users by sending the dedicated beam to the each users, right? And also we can scan the beam if you have a user is not stationary or if it's moving, and continuously trace the users, right? So this can be realized, this kind of antenna can be realized using the some kind of array of antenna, then using the some kind of beamforming network. So you can see here, this is the multi-beam antenna system where 4 elements are used. That's combination of hybrid or phase shifters by using appropriate number of couplers and phase shifter. We can have the multiple number of beams by inserting different ports. We can have the different number of beams. Okay, or by inserting all ports together, we can have the multiple beams. So this is the one design of the 4 element MIMO antenna to generate 4 number of independent beams. So this is the array of 4 dipole antenna, then different natural coupler, then some kind of delay or phase shifter, and this can see the 4 ports. By inserting different ports, you can have the 4 number of beams with highly directed behavior. So then briefly, what is MIMO? So MIMO technology refers to the use of multiple transmitting and receiving antenna at the transmitting and receiving end, right? So that signal are transmitted and received through multiple channels to improve the quality of service, right? So using this concept of MIMO, we can see here this is the MIMO system where we have the multiple transmitter or multiple antenna, and we have the multiple receivers. So you can see each receiving antenna receiving multiple beams, right? So suppose due to some reason one signal is lost, maybe there's a chance that your receiver receive the signal from the channels, right? So basically, while designing a MIMO, it is designed mainly for two objectives. One is a reliability by using spatial diversity, and second is to have the high throughput or high speed data using the spatial multiplexing. So in case of reliability, we send same signal, I mean, using the multiple channels, signal using the multiple antennas. So we have that some kind of redundancy. So if some one signal is lost due to fading or due to some other obstacle or due to some blockage, there is a chance that your signal will be received by the receiver. So this way we can enhance the reliability of the communication. On the other hand, we can also have the high throughput. Suppose we have the long stream of the data, right? By sending the long stream of data, it will take time, right? So what you can do, you can just segment the entire bit stream into small segments. So we all, and these all small segments can be transmitted simultaneously by the number of antenna elements. So this way we can transmit this high stream data bit by in very fastly, right? But while doing all these things, we have to keep in mind that this antenna, this nearby antenna or this adjacent antenna should not talk to each other. So we should require very high isolation between these two antennas. So how we can ensure by how we can quantify this by using this ECC, or we can say anode correlation coefficient. So while designing MIMO antenna, you have to keep in mind to maintain high isolation, your ECC should be very, very small. Then we can have the diversity gain, while I mean each antenna should provide the optimal gain while combining the antenna, right? So there are few solutions are made for this to cover this millimeter wave 5G application. So this antenna basically 4x4 MIMO antenna designed for this 5G application. So this is a Vivaldi antenna, and there you can see there are 4 ports are there. But you know, Vivaldi antenna is basically generally used for wideband applications. But you know, we are talking about the millimeter wave 5G applications, so you know it has a limited coverage or a limited range, right? So, and because of the high losses at high frequency, so this kind of system should be required very high gain, so it can cover the long range, right? So to cover this, we use some kind of gain enhancement technique. So here, this meta surface is being employed to enhance the gain of this conventional Vivaldi antenna. Also, not only gain, it will also help to provide the improve the isolation between these two antennas, right? So that dual fold purpose to have this meta source, I mean, enhances the gain of antenna and also to provide the high isolation between this adjacent elements. You can see this is the spectrum response. You can see we have the high isolation that's below 20 dB and with good matching. Then you can see here that is the gain response. So what is happening basically by employing this meta space, we can basically provide a very high coupling to the electric or this fields from the radiating from the Vivaldi antenna. So you can see this is a strong coupling between the fields radiating from the Vivaldi to the metal surface. So with this way, we can confine your fields within the particular direction in this direction by using this metal surface. So you can see the improvement in the gain. This gain is improved from 6 dBi to close to 11 dBi after this incorporation of this metal surface. And this is the 2D pattern. So before the and deploying this meta surface and after deploying the meta surface. So before this, you can the antenna isolation is very, very poor. It's try to interact with these two. They will, I mean, the antenna one antenna will try to interact with each other because of the way the beam is there. But because by employing this meta surface, we can enhance the gain and simultaneously your isolation will also improve. Good. So as I mentioned, this efficiency is very, very crucial factor while working at high frequency. We always try to minimize this power loss at high frequency. So we can replace your metallic antenna by the this non-metallic DRA, and also this gain enhancement structure by using the non-metallic gain enhancement structure. So here we have used this insulator or dielectric cavity to enhance the gain of the antenna. You can see this is the array of 4 DRA antenna. They are connected to each other to minimize the isolation, right? And isolation will also be improved by the gain enhancement technique like this. So this is the top view of the this antenna. So this we can see the gain improvement in the compared to the earlier structure. So here without this horn, gain is same like earlier. Vivaldi antenna, it's close to 6 dB, but after using this this cavity, this DRE cavity, this gain is significantly improved to close to 21 dBi, right? While maintaining the efficiency like earlier case. So yeah, this is the pattern of the antenna. So you can see here without this horn, you can see that this is the radiation pattern. Okay, so it's very difficult to maintain the isolation, and this will have limited coverage, right? Limited communication range. So by using this horn, we can significantly enhance the gain, and this will improve the isolation and also communication range. It will compensate the losses because of the other many factors. Now, massive MIMO. So, or this is not only about the number of elements; it's also about some other technology or integrated technology like beamforming or phased array antenna systems, right? So, what is massive MIMO? So, massive MIMO is an, you can call it extended version of MIMO technology, where 100 or even thousand of antenna are combined and integrated with beamforming or phased array technique at the basis to increase the um, quality of service or to utilize this available resources more fruitfully. I mean, we can enhance the spectral efficiency or throughput of the system, right? So this is the scenario for the 4G, right? So you can see here we have number of devices around the base station, right? So suppose this user wants to connect with the base station, right? When multiple devices are there, so using the 4G, we can connect only one device. We can connect. We can, if you are connecting this device, because the type of radius is there, this will be also try to send the signal to the other undesired users, right? So it's a total wastage of the energy, and also at the same time, it will not be able to cover the users which are far located away from the base stations, right? But using the concept of this fifth generation technology or massive MIMO, you can see just the scenario of the this I mean this massive MIMO, right? So we can send the dedicated beam to the different users located at the different locations, right? So this way we can enhance the, we can save a lot of power, right? We can serve the user independently or customizedly. We can serve the user, right? We can also enhance the quality of service using this concept. And you can see here, this is not about the number of elements or massive MIMO. It's about the integration of other technology uh, like active phased array antenna array, like array, active phased array antenna, right, or other kind of system like RIS or other systems. So how to go for the meshing MIMO? So slowly we're moving to the utilize the meshing kind of thing. So we have increased the number of elements from 4 cross 4 to 8 cross 8. So you can see here the number of elements are increased to 8, right? And to enhance the gain or to enhance the isolation, we have we have loaded the each antenna by vertically placed number of layers of this meta surface, right? So this meta surface will help to enhance the gain of the antenna. And what is additionally here, we can control the number of the gain of antenna by controlling the number of layers. So I suppose we are using one layer, that gain will be less. If you are using all layers, we can have the higher gain. So by this we can cover the users close to the antenna or users which is far away from the antenna, from the base station. I mean, we have the adaptive kind of gain from this system, so controlling the number of layers, maybe 3 or maybe 1 or maybe more than 3, right? So this is the scenario of the radiation from the antenna without loading this meta surface, and this is scenario after loading the meta surface. So you can see here, after loading this with the number of 3 layers of metal space, the gain is drastically enhanced. The beam is more converse in this direction, right? And you can see the gain enhancement. Like earlier case, we have the from 6 to again close to 11 dBi, we can have the gain enhancement, right? But we can cover more number of features with this concept. Now we can extend our design to the 16 cross 16 or maybe 30 cross 32 MIMO entry systems, right? So now we have a 16 number of elements, and this is the beam 3D reducing pattern of the. So you can see here the beam is highly focused while maintaining the all other parameters within the limits, right? So your matching is maintained, your isolation is also maintained. Yeah, so this is another technology which will be play key role in case of 5G or beyond 5G communication technology. So multifunctional antenna, or we can call it conventionally reconfigurable antenna. So I mean the concept is we require the antenna which can change the operating characteristics electronically, okay, or electrically. So I mean it can serve the user as per the requirement of the system. So this kind of system provide multi-functional right. I mean the same system can be utilized to have the we can change the frequency, we can change the polarization, we can have the uh, diverse radiation pattern, or maybe we can combine more than 2 parameters. We can combine all three to have the compound or hybrid kind of reconfigurable antennas. So what is required for to to realize the reconfigurable antenna? So we required some kind of switching elements. The switching element may be electrical switching, or maybe optical, or maybe you can have the physical alteration in the device or in the antenna. Then we can change the material of the antenna to make it reconfigurable. So there are few circuits, actual circuits we designed to have the reconfigurable antenna. So this is a pattern reconfigurable antenna or pattern scanning antenna. So here 3 dipoles are used, which are connected to the your feeding line using the 3 diodes. So by making the diodes on and off, we can have the different number of beams in the different directions, or one beam in the different directions. For example, if you excite this dipole, your beam will be in this direction. If you exciting dipole 1, your beam will be in this direction. Or if you excite both the dipoles, in that case, your beam will be in this direction. So by exciting one diode at a time, or maybe 2 diodes at a time, we can have a 6 number of beams in the different directions. So this way we can have the reconfigurable pattern scanning antenna, where your pattern can be scanned in the different directions. And it is required like in case of 5G technology. Right. So then second is, as I mentioned, sometimes the user location is different. Maybe sometime user may be close to the your base station, or maybe away from the base station. In that case, no need to suppose your user is close to the base station. In that case, no need to send the high gain signal, right? So maybe low gain will be suffice the purpose. So we can have we can provide the better coverage to the users, different users, right? If your user is close to the antenna, we can cover more number of users, right? So this way, by this concept, we can have the concept of reconfigurable beam shaping. So you can see this is a typical very traditional kind of series feed array. 3 elements are there. So by connecting 2 elements to the first element, or by making on and off this diode, we can form an array, or maybe a single element will be activated by, we can have the 2 different states, beam with high, with the low half power beamwidth, or large half power beamwidth, or high gain or low gain. So this way we can have the concept of reconfigurable beam shaping antenna. Then also we can scan the null of the antenna, right? And this is very much required. like in case of no, suppose you want to hide yourself from the hostile users, or suppose you want to hide your aircraft from the radar, right? So you always try to create some kind of null in the direction of your radar signal. So this way you can hide yourself, or your radar will not intercept your systems, right? So and your direction may be anything, right? So you can first to create the null in the direction of your hostile systems. Then your null should be movable, or should be the direction we can change, right? Because we know the direction of incoming signal. So your system should be capable to change the direction of null. So this way you can hide yourself from the different direction by creating the null in the different direction. So this can be done by using this kind of antenna. It's basically two slot array antenna, and there's a cavity, and beneath this, uh, inside this cavity, there is a feeding network with a different number of diodes. By activating this providing phase delay to these slots, we can scan the null by making these four diodes on and off, right? So this we can have the null scanning antenna. Besides, we can also have the polarized and reconfigurable antenna. So again, it's a very conventional kind of a patch antenna, and this very conventional technique by truncating the different four corners of this patch antenna, we can have the different polarizations. Like we can have the left hand polarization, we can have the right hand polarization, or we can have the linear polarized wave, right? So by making these two diodes off, right, we can have the right hand polarization. By making these two corners off, truncated, or these two diodes off, we can have the left hand polarization. Or by making these four diodes, or by truncated four diodes, or by making these all four diodes on, we can have the LP radiation from this antenna by applying proper biasing conditions. And this is the kind of diode being used in this antenna. So we can see this is the performance of this is the axial ratio for the RSCP and LSCP. This is well below the 3 dB, which is the requirement for axial ratio. And this is the case of linear polarized wave. So you can confirm that your antenna is transferring CP and LP perfectly. Then we have kind of no active antenna. You can integrate the active devices like amplifier or oscillator into the antenna itself to I mean minimize the losses because of the long cables or because of the interconnects, right? So this way we can have the highly efficient antenna or high gain antenna. I'm not going much into detail of this antenna, but the concept is by minimizing the losses due to the interconnecting cable, we can get your misactive device into antenna itself, right? So like in case of your inability, suppose you're incorporating the oscillator, this antenna can act as a radiator, also as an oscillator also, right? So on the same platform, we can integrate the antenna as well as the oscillator or amplifier. Then we have the concept of rectifier integrated antenna. So in case of 5G and 6G technology, right, there are concept of internet of things, right? We have so many devices connected, right? Then we have the sensors are there, or wearable devices are there, and all these devices are basically rely on for the power, they are rely on the battery. And the battery has a limited life, right? So maybe after some time the battery will be adjusted, right? So you need to recharge the battery, or right, you need to replace the battery, right? And this is very, very inconvenient or not practical sometimes. Suppose in case of this implantable devices for healthcare, it's not every time feasible to remove the device and to replace the battery. So the point is it possible to make these devices, IoT devices, or these sensors, or this implantable devices, battery free, or autonomous in terms of power requirement? Okay, so the idea is we can utilize the existing, available RF energy to convert the signal, and convert into DC, and to power these devices, these wearable devices, and these IoT devices, or these sensors, to provide the power in continuous manner without any interruption to the service of the user, right? So this is the kind of antenna which is integrated with the rectifier circuit. So it is called basically rectifier integrated antenna. And also this the power which we usually get from this kind of system or after rectification is very less, right? So the idea is it possible to capture the RF signal from the different frequency bands, right? So we can enhance the DC power output DC power. So the idea is we can have the multi-band antenna or maybe wideband kind of antenna, so we can capture the RF signal from the different frequency bands from different RF sources and harvest them all together to convert into DC. So this way we can enhance the DC power. So this is the typical multi-band kind of rectifier integrated antenna. So you can see this is the multi-band antenna response, and you can see here it's a dual band kind of rectifier system. So this is the DC output for the two bands for a GSM band and for 3G band 2.1 gigahertz. We have targeted GSM signals because the availability of GSM signal is very high and strength of GSM signal is high compared to the higher bands like 2.1 or other frequency band. So you can see here, since the available power, RF power is relatively large, so we can have the higher DC output voltage compared to the 2.1 gigahertz. So this is the plot of DC output over the different input signal, different input power level. And this is the efficiency at two bands, right? So you can see we have higher efficiency at GSM band compared to the 3G band. And this is the wideband rectifier antenna. So you can see here, this is the S11 of this wideband antenna. And for antenna purpose, we have again replaced this metallic antenna by using the non-metallic DRA antenna. So we can minimize the losses, conductor losses up to some extent, right? Using this DRA antenna. So you can see here we are harvesting energy from the different frequency band. 1.8 gigahertz, that's again GSM band, then 2.1 gigahertz, 3G, then 4G, then your 5G, I mean, or WiMAX, 3.6 gigahertz band, right? So you can see this is the DC output voltage for the different frequency bands. Yeah, so this is a rectifier integrated antenna where you can power the devices autonomously. Yeah, then we have, I mean, you maybe all are very much, I mean, enthusiastic about the concept of RIS, basically RIS. So again, the purpose is same, like in case of reconfigured antenna or multi-beam antenna, but the purpose is basically to send the signal in the desired direction to cover the desired users, right? But here, basically, the antenna is not there. Only we have to use some kind of intermediary structure which rely on the incoming signal and will manipulate this incident signal as per the user requirements. Right. So this we can, I mean, by designing the RI surface, we can manipulate the incoming wave or incident wave to send in the desired direction, right? So what is this RIS? So RIS are the planar array of the, and this extension of the metamaterial basically. It's basically we can call it 2D metamaterial, right? Or meta surface. So these are the basically densely distributed metallic patch called meta atoms, right, of sub-wavelength, right? They are basically positioned in the periodic manner and integrated with some kind of switching elements like varictor diodes or pin diode or MEMS kind of elements. And it has unique property to manipulate the special property like radiation pattern of the incoming or incident wave on its surface, right? So these are the unit cell of this RI surface. It is integrated with some switching elements, right, and supported by some kind of substrate. So by making these devices, these active devices, by tuning these devices, we can change the surface of this surface, and accordingly we can change the phase of your outgoing wave. So it can be transmitted in the different directions, right? So this is the use case scenario of this RIS. So you can take two cases. Case one, this is the cell tower. this is the user, where suppose this user wants to communicate with the cell tower, but because of this building, there's a non-line of sight situation is created, and because of this, the signal will be blocked by this building. So there's been no connectivity between the user and the cell tower, right? So to provide a seamless connectivity to this user, what could be done? So the arrays can be mounted on the building, nearby building. Okay, so this arrays will sense the cell tower location and also the user location, and will sense this user that is not getting the signal. So it will provide some kind of no alternative link to the users, right? If it is the main link is blocked by the some obstacle, right? So this arrays will provide the auxiliary LOS link to the users. So it will provide the continuous connection to the this user. This another case is this, where there are two users. One is our desired user or an intended user, and second is basically undesired user, right? So the purpose to maximize the signal strength at this user and to minimize to create the null at this user. So how can it can be done? So this arrays again sends the user location, right? Desired user location. So it will provide the indirect signal to this location, which will be in the same place as the main direct signal. So it can create the this kind of interference between the direct link or indirect link. So the signal will be maximized. On the other hand, in the direction of undesired user, it will create the kind of some destructive interference. So the net signal will be zero or none will be created. So this user which is undesired will not receive any kind of signal. So this way we can create the point is we can send the beam in the particular direction and can create the null in the undesired direction. So we can cover the different features. And this can be done. This RS basically planar surface can be easily on the device buildings or maybe some other platforms easily. So this is the one actual RIS taken from this article. So you can see here these are basically 10 cross 10 RIS. These are the meta atoms or units of the surface, and you can see here this is basically integrated with the switching elements, right? So by making this diode, by providing appropriate biasing to this diode, we can control the phase of the each diode, and we can control the overall the system. So we can have different phase combination. By having different phase combination, we can have the different direction of the outgoing waves from the surface. So you can see here, suppose this is the direction of your incoming wave, maybe the outgoing wave, reflected wave beam will be maybe in this direction, right? Or maybe in this direction, or maybe in different direction, depending on the biasing condition of the different directions. So this is the, you can see this is the uh, um, direction of incoming wave, and this is the direction of outgoing wave, right? So this is the reflected signal for when incident signal is at 58 degrees, this outgoing signal at 150 degree. Also, we have to ensure this angular reciprocity, right? Suppose that we change the direction of suppose I change the direction of incoming wave to this direction. In that case, your beam should be reflected in this direction. So while making this kind of RA surface, you can also check for this angular symmetry or polarization. I mean, what kind of polarization is there, or we can check also for the angular reciprocity or angular stability. I mean, depend on the from suppose that the direction of incoming wave is different. I mean, the same level is maintained or not, we can check it. So while fabricating, suppose you have developed RIS, how we can measure this RIS surface. This is the test setup to measure the RIS. So this is your RIS surface, and you can excite your RIS by using the typical low standard horn antenna, and this will be excited by the RF signal. And this biasing can be controlled by using the computer or by using the controller or MBG controller. We can change the biasing of the diode and or phase of your RIS system, and you know the direction where you want to reflect your signal, and accordingly will decide the phase of the RIS, right? But how we can ensure that the way for what direction we design this RS, you can check with this receiving horn antenna. So you can rotate this horn antenna and you can receive the reflected beam out of your RS, right? So suppose you have designed for, let's take for 45 degree angle the reflected beam. You orient your receiver antenna in the 45 direction, and your receive signal should be enough or should be high to ensure that yes, your RS design is correct because your beam is reflected in that particular direction. So this way you can ensure that your eye is properly designed or not. So this is about the RIS. Then what are the future technology for 5G and beyond 5G communications? Right. So these are the few technology for 5G and beyond 5G communications. So this fluid or a liquid or mobile or we can say flexible antenna system. So by like earlier cases, we are using the diodes or active devices, right, or some physical alteration, right? We require the multiple antennas or beam forming network or phased array antenna if you want to focus the beam in the particular direction, if you want to scan the beam in the desired direction, right? But also we can use this concept, right? We can use some kind of some liquid, right? So no need to provide some kind of switching elements. So by controlling the flow of this liquid material or this conductive material, which is fluidic or maybe liquid, we can change the different parameters as per the requirements. Like so, again, we can change the gain or radiation pattern or operating or other property by using this concept. So this is very, new concept which is maybe um, in trend, trending right nowadays. Right. Then we have the terahertz antenna systems. So by talk about the terahertz antennas, the frequency target from 1.5 sub-terahertz frequency from 0.1 to 1 terahertz. So as you know, that's we are actually very high speed from the 6C technology, right? So we expect if you are using the terahertz frequency, we can expect huge speed from this terahertz based 6G technology, right? Or we can have the concept of antenna on chip or IC systems, right? So because system size will be very small while working at the high frequency. So we can have the concept of antenna or antenna on chip or array. Because at low frequency, the size of array will be very large, but at terahertz, we can have the accommodate more number of elements, right? Like in case of massive MIMO, here we can also even accommodate more number of element compared to the massive MIMO or MIMO concept, right? So we can have the huge bandwidth to match with the high speed communications. And also we can have the concept of joint communication, like or com sense antenna, which can communicate and sense at the same time. Or if conventionally we require the separate antenna for the sensing application and for the communication application, which uh, will enlarge the size of your system, right? So to make the system more complex, we can have this concept which can same antenna can be utilized for the communication or for sensing applications. So radiator which can sense the environment intelligently, right? It's not simply sensing and communicate. It's about how intelligent can communicate or sensing the systems, right? So we can integrate with some intelligent and concept like AI or some other machine learning technique to make it more intelligent, right? So you have to make the system more autonomous, right, or intelligent. So it can communicate, it can transmit without any human intervention or manual intervention, right? Then we can also have the concept of hybrid radiating systems, right? So now you can see we have the 4G system, we have the 5G system, we have the 6G system, right? And they are different in terms of infrastructure, different of RF front ends or technology, right? So the idea is it possible to combine all this technology? So no need to change the current infrastructure, right? Significantly. So this way we can save the cost or infrastructure requirements. So the idea is it's possible to have the hybrid kind of antenna system. So we can incorporate all three different technology, right? So this is all about the future antenna technology. Now, briefly about the development of antenna while designing antenna for any technology like GSM or whatever, or 5G or 4G or 5G technology in general, what should we keep in mind while designing the antenna? So the material, right? So material while designing antenna, you have to keep in mind what material will be most appropriate for the particular application. So there are different kind of materials are available, or dielectric substrates are available like RT rod or FR4, or you can use Teflon, alumina, or quartz, or foam, or GML, or you can use this SiO2 material, or maybe compound kind of material, right? So typically, if you are targeting antenna, right, you always prefer the low dielectric constant, or thick substrate is always preferred. So we can have the efficient radiations, or right, or we can have the, I mean, quite broad bandwidth operations. This you can answer by using low dielectric constant or thick substrate. While on the other hand, suppose you are making the guiding structures like filter you are making, or making transmission lines, or maybe you are making couplers. In that case, it's not preferred to use the low dielectric constant or thick substrate. Instead, you can use the high dielectric constant, or you can use the thin substrate. So it can carry the energy, it cannot radiate the energy, right? Or it will can confine the RF signal to within the structures. Then, if you're for antenna, you can use the metal, or copper. You can use the silver or gold, right? If you are making the metallic antenna, or you can also use the non-metallic antenna by using the DRA, or ceramic kind of uh, substrate you can use for the antenna. Okay, so next, if before going for the fabrication, you wanted to predict the response of your antenna. So you can use the different kind of simulator to estimate the or prior estimation of the of your design, what kind of performance your design antenna will give. So you can predict the response by using the different kind of softwares like CST, or HFSS, or I3D, or Momentum, or FECO. There's many software are available in the markets. If you are focused on the kind of active integrated antennas, you can use the EDS. You can have the full simulation of active circuit, or antenna, right? Passive parts of the antenna systems, or you can use the AWS softwares. Then for fabrication, there are so many techniques are available, like lithography. That this is very conventional technique which can use the chemical etching, right? Or you can use the non-chemical techniques like milling machines, or computer-based technology like CNC, or laser-based printer are available, or you can use 2D or 3D printer. Like in our case, we designed that antenna. That's basically 3D printed antenna. This whole antenna. So you can use this by using this kind of printer kind of technology, or printing kind of technology, you can save a lot of material, or a lot of time you can save, or it will be more cost effective compared to the conventional technology. And then laser prototyping technology is also available. Then ultimately, once your design is ready, your fabrication is ready, you would like to test your antenna. Okay, so it can match with what you intended to do. Right, you can do measurement by using VNA vector network analyzer, or you can use the signal generator, or you can use the spectrum analyzer, or for in case of antenna, you also require the anechoic chamber, right? You have the accurate measurement of the radiation pattern by minimizing the unwanted reflection from the different objects, right? Then suppose you are working on the terahertz frequency, or millimeter frequency, right? The size of antenna will be very, very small, maybe in the form of chip, or maybe form of the dial, right? In that case, it will be not possible to measure the performance of antenna. Is the measurement setups, okay? Like conventional connectors. So what you require the probe stations. So you can directly mount these probes on the antenna itself. You can measure the all kind of parameters from this kind of. So this is very useful for while designing antenna for very high frequency applications, right? Or you have to making the antenna like using SiO2 substrate, or like glass substrate. Right? Then if you are measuring the performance of antenna in time domain, right? Like in case of ultra wideband antenna, you always would like to see the behavior of your received pulse from the antenna, right? Whether your pulse shape is maintained or not. In that case, you can use the high frequency uh, digital oscilloscope for the time domain analysis of your antenna, right? So this is all about the talk. Okay, so with this, I thanks all of you listening my talk. I hope you will enjoy this talk. Now, if you have any doubt, the session is open for the query. Okay, if you have any query, please let me know.
Thank you, sir. Thank you for delivering a special talk on 5G and beyond 5G technology, IoT, active antennas, rectifier integrated antennas, and some future antennas technology. Participants, if you have any doubt or query, you may ask the sir on the chat box. Sir, there are some participants' doubts here in the chat.
Okay.
One, the first comment is from Afrin Khan. Sir, metamaterial implementation is increasing gain and providing the isolation. What is the methodology behind it? How metamaterial structure are doing this?
Yeah. Yeah, very good. Okay, so basically, as I mentioned, the purpose of this metamaterial to provide the desired phase, right, from the outgoing waves, right? So by this, by using the concept of metamaterial, we can change the phase of the outgoing wave. So we can send the signal in the particular direction. We can compensate the phase of the signal to create the null in the particular direction or to make the signal in the particular direction, right? And the second point, how it is helpful to enhance the isolation, right? So again, so to enhance the gain, what is required basically? We have to focus the beam in the particular direction and to create the null in the other direction, right? So to provide the appropriate phase, right? So beam, I mean, you can have the destructive interference or constructive interference, right? So by manipulating the phase, we can have the constructive interference where we can create the maximize your radiation pattern. I mean, you can maximize the gain of the pattern or your antenna, right? And in the other direction, you can have the null. So it's all about the phase, which we are doing with the unit cell, right? We can have the design unit cell to provide the required phase, right? And also by proper coupling of the electric field to these unit cells, we can design your unit cell in a such a manner by controlling the inductive or capacitor, right? Or so this way we can change the material of your unit cell, right? So by changing the material, we can tightly couple the fields in the particular direction by this metal surface. And if you suppose, just think of if the beam is highly focused, it will not know, it will not interact with the nearby users, right? Because the beam is highly focused. So this will also help to enhance the isolation of the your MIMO systems, right? So it's all about your creative design reflection from your metamaterial or meta surface. Okay, so we are basically this we can create the you can enhance the gain of the antenna and you can create the null in the desired direction. And this can be done by using the by designing your unit cell appropriately. So this all about the inductor and capacitor of the unit cell. By controlling that, this we can enhance the coupling of electric field and your unit cell.
Okay.
So I hope the query is answered. Anyone else?
Yes, sir. The next question is how to start working for fluid antenna for 6G application.
Yeah. So it's not about the antenna. Antenna is same for all the kind of technology. It's about what are the key technology behind the 6G antenna, right? So first you see the frequency, right? Suppose your frequency is very high, then you have to keep in mind the material which we are going to use because you have to minimize the losses frequency, right? Then second thing, the gain should be high, right? So to have the high gain, you need to apply the concept of this gain enhancement techniques, like this metamaterial or meta surface. Then it's about the technology, basically technology which are going to use to basically support the 6G technology. Okay, then you can think of the MIMO systems. Okay. So these are the key technology behind the 6G technology. Right? Otherwise, the antenna design is same like earlier technology. So there's no change in the if you're designing a single antenna. It's about the application. If you're talking about the high frequency, it's all about the material. You choose the material appropriately, then what technology you are going to make it, right? You can have the MIMO system, you can have the massive MIMO system, you can have the multi-beam antenna kind of systems, right? Or you can have the reconfigurable antenna kind of systems. So these all key antenna technology which are will support the 6G systems or 6G technology or 5G technology also.
The next question is how
Yeah,
can we how can we fabricate antenna if antenna size is very small? And the second question is similar to that one. Can you provide some contact where the fabrication and measurement facilities are available?
yeah. So I mean, very small antenna. I mean, you are talking about the very high frequency, right? Maybe millimeter wave or terahertz frequency, right? So if you are working on the millimeter wave, up to some extent, it can be fabricated with the existing this conventional milling machines. And the many vendors are there which provide the this machines like maybe aware about the LPKF or MITS, right? This machine fabrication machine can be work up to millimeter wave. They can print the circuit, right? But if you're going to like terahertz frequency, right, then this machine will not useful, right, to make this tiny small antenna, right, or small antenna. In that case, you can go for the laser-based kind of fabrication prototype machines, like so, or like CNC machine you can, right? So again, let's say LPK provides two kind of machine. One is milling machine, which is basically mechanical kind of machine, which can work up to up to 20 gigahertz or with more. I mean, precision you can use up to it can go up to millimeter wave frequency, right? Or there's another kind of machine which again this LPKF UK provides. This is basically laser-based prototyping machine. And by using this laser-based prototyping machine, you can go up to the terahertz frequency. You can design very fine tracks or very small antenna, right? So I'm giving one reference. There's a laser-based prototype machine is available at IIIT Jabalpur, and also this second machine, this LPKF milling machine, also available at IIIT Jabalpur, right? Also, there are some vendors are available are there in the market. You just give the your design circuit, I mean your CAD file of the your antenna, and you can just send. They will give the quotation, they will give the estimate how much the cost of your antenna, right? So you can, there are many vendors are available, maybe in the Gandhinagar or maybe in the Delhi. They can fabricate your antenna design, whether it's small or large, right? And if you're going for the like SiO2 antenna, that's very difficult, right? So foundry is not able to work on the very high frequency, like 100 gigahertz frequency, right? Or SiO2 technology or antenna on chip. That's difficult to fabricate in India, right? But still institute like IIC Bangalore, they are working on the semiconductor technology. They are like sense facilities there, so you can talk to them. They will even fabricate the very small kind of antenna in the form of maybe in the form of die or antenna on chip, right? So many vendors are there; they can help you.
Okay. Next question is related to absorbers. In
Uh-huh.
designing in designing an absorber using metamaterial, impedance are matched. Then why it is absorbing?
Now, how impedance is matched? So impedance can be, you have to provide the impedance matching, right? Because the impedance of a space is different, impedance of your meta surface is different. Okay, so to ensure that is a perfect matching between the your incoming wave and outgoing wave by properly designing your meta surface, you would say.
Okay.
This is the
For
purpose, right? While manipulating your wave, you have to keep in mind that your matching should be good.
next query is for 6G antenna, what material we should choose? Is it RT Doroid?
Yes, suppose you are working on this millimeter wave frequency, you can use RT Durot, right?
And his next query is, as RT Duroid is expensive, what should be alternate for this?
What will be alternate?
For this, for RT Duroid.
For alternate, maybe this Neltec may be alternative for this FR4. I mean, not for FR4, for this RT Duroid. This GML Neltec, it's maybe alternative for this FR. I mean, this RT Duroid.
Okay. In India, up to what frequency we can fabricate antenna for 6G?
In India, we can fabricate this millimeter wave antenna, you can easily fabricate. Even you can fabricate up to 0.1 terahertz also. Because you can see the design of the what I have presented, you can see here. These all designs are fabricated in India, right? These all designs. These are millimeter wave antenna for 5G applications. These all are fabricated here. Okay. So yes, it is true. It easily fabricated. Any other query?
The last query, sir. Good afternoon, sir. Very useful talk, sir. As a newcomer in antenna designer, how to explore more domain knowledge in this area, sir? Can you please suggest some guideline suggestion with
Yes.
respect
So as
to
I mentioned in the last slide, these the topics you can, I mean, focus while designing antenna for upcoming technology, right? So you can work on this flexible kind of antenna, right? You can work on this textile kind of antenna or conformal kind of antenna, right? You can also work on this is very interesting topic like this a rectifier integrated antenna, right? Because as I mentioned, there are so many devices are available in the I mean the systems or IoT devices are available, so that the battery is very I mean challenging part, right? To replace the battery every time. So you can work on this rectifier integrated antennas. Then this you can also use this ComSen antenna, which can use for communication or sensing applications, right? And then this terahertz antenna system, it is also very, I mean, gray area where you can work on. And then hybrid radiating systems. So these are all areas you can think of or can start working on this area.
okay, sir.
Okay.
Okay, thank you, sir, for delivering a special talk in this FDP and taking all the participants' doubt seriously. We truly appreciate your time, effort, and willingness to share your expertise with us. Once again, thank you so much, sir.
So if you have any further query, you can just drop a mail on this email ID or you can contact me on this mobile number. Okay, so thank you so much.
Okay, thank you, sir. Thank you
Thank
for
you.
that. With this, we conclude this session. We will now take a lunch break, and next session will be begin at 4 p.m., which will hands-on session. Thank you, participants. Thank you all.